What if I told you that you've never actually touched anything in your entire life? Not your phone, not your loved ones, not even yourself. And the reason has everything to do with why touching a photon is one of the most mind-bending questions in all of physics. In the next 3 hours, I'm going to take you on a journey that will completely change how you see reality. We're going to explore a question so profound that it reveals the fundamental weirdness of our universe. And by the end, you'll understand why the simple act of touching a photon exposes the bizarre truth about matter, energy, and the very fabric of spacetime itself. Here's the thing that's going to blow your mind right from the start. You can't touch a photon. Not because it's too small or too fast, though it is both of those things. You can't touch a photon because the very concept of touching breaks down when we're talking about light. But here's where it gets really crazy. The reason you can't touch a photon is the same reason you can't actually touch anything else either. What you experience as touch is actually electromagnetic repulsion between the electrons in your skin and the electrons in whatever you think you're touching. You've never made contact with another object in your life. You're floating through existence, separated from everything by impossibly tiny distances governed by quantum fields. But we're going to go way deeper than that, because when you really understand what a photon is and why touching one is impossible, you unlock secrets about the nature of reality that most people never even consider. We're talking about the wave-particle duality that makes photons both everywhere and nowhere at once. We're talking about how light doesn't experience time. We're talking about the quantum weirdness that means a photon exists in a superposition of all possible paths until the moment it's observed. And we're going to explore what it would actually mean to catch a photon, which happens every time light hits your eye, but in a way that's far stranger than you've ever imagined. Before we dive in, do me a favor. Hit that like button and subscribe, because what we're about to explore is going to challenge everything you thought you knew about reality. And I want to know where you're watching from and what time it is there. Drop a comment telling me your country and your local time. I'm curious how many of you are watching this at 3 in the morning because you fell down a physics rabbit hole. Trust me, by the end of this video, you're going to see the world completely differently. Let's start with the basics, but I promise you, even the basics are going to surprise you. What is a photon? Most people would say it's a particle of light. And that's sort of true, but it's also sort of completely wrong. A photon is what we call a quantum of electromagnetic radiation. It's the smallest possible packet of light energy. But here's the first twist. Calling it a particle is misleading because it doesn't behave like any particle you're familiar with. The story of understanding light is one of the most fascinating in all of science. For centuries, scientists debated whether light was a wave or a particle. In the 1600s, Isaac Newton argued that light must be made of particles, which he called corpuscles. He had good reasons. Light travels in straight lines, casts sharp shadows, and bounces off mirrors predictably. All things that made sense if light was made of tiny particles zipping through space. But around the same time, a Dutch scientist named Christian Huygens proposed that light was actually a wave, like ripples on water. His wave theory could explain things like refraction, how light bends when it passes from air into water. For a while, Newton's particle theory dominated because, well, he was Newton. But then in 1801, a British polymath named Thomas Young performed one of the most important experiments in the history of physics, the double-slit experiment. Young shone light through 2 narrow slits onto a screen. If light was made of particles, you'd expect to see 2 bright lines on the screen, one behind each slit. Instead, Young saw an interference pattern, alternating bright and dark bands. This is exactly what you get when waves overlap. Where wave peaks meet wave peaks, you get brightness. Where peaks meet troughs, they cancel out and you get darkness. This seemed to prove definitively that light was a wave. Throughout the 1800s, Physicists like James Clerk Maxwell developed a complete mathematical description of light as electromagnetic waves. Maxwell showed that light was oscillations in electric and magnetic fields, rippling through space at a constant speed of about 300,000 kilometers per second. Everything made sense. Light was waves. Case closed. Except it wasn't, because in 1900, something happened that would shatter this comfortable understanding and launch us into the weird quantum world. A German physicist named Max Planck was trying to solve a problem about how hot objects radiate light. The existing theories predicted something absurd called the ultraviolet catastrophe, which suggested that any object at any temperature should radiate infinite energy in the ultraviolet range. Obviously, that doesn't happen. Planck discovered he could solve the problem if he assumed that light could only be emitted or absorbed in discrete chunks, which he reluctantly called quanta. The energy of each quantum was proportional to the frequency of the light, with a tiny constant of proportionality that we now call Planck's constant. Planck himself didn't really believe light was quantized. He thought it was just a mathematical trick. Then in 1905, a young patent clerk named Albert Einstein took Planck's idea seriously. Einstein was thinking about something called the photoelectric effect. When you shine light on certain metals, they emit electrons. But here's the weird thing. The energy of the emitted electrons depends on the frequency of the light, not its intensity. Bright red light won't knock out any electrons, no matter how bright it is. But even dim ultraviolet light will do the job. If light was a continuous wave, brighter light should always produce more energetic electrons. But that's not what happens. Einstein explained this by proposing that light actually comes in particle-like packets, each carrying an energy determined by Planck's formula. A single packet of high-frequency light carries more energy than a single packet of low-frequency light. This is what we now call a photon. Einstein won the Nobel Prize in 1921 for this work, not for relativity, which most people assume. And here's where things get truly strange, because experiments kept showing that light behaves like a wave in some situations and like a particle in others. It's not that light is sometimes a wave and sometimes a particle. It's that light is something else entirely, something that exhibits both wave-like and particle-like properties depending on how we observe it. This is the famous wave-particle duality, and it's not just true for light. It's true for all quantum objects, including electrons, atoms, even large molecules. Think of it like this. Imagine you've lived your whole life in a two-dimensional world, like a drawing on paper. Then someone tries to describe a three-dimensional sphere to you. From one angle, it looks like a circle. From another angle, it still looks like a circle. You might argue about which type of circle it is, but the truth is, a sphere is something your two-dimensional brain can't fully visualize. It's something more than just a circle. A photon is like that. It's something that exists in a way our everyday intuitions can't fully grasp. When we measure it one way, it looks like a particle. When we measure it another way, it looks like a wave. But it's actually something that transcends both descriptions. Now here's what's going to set the stage for everything else we talk about. A photon has zero mass. It's massless. And because it's massless, it always moves at the speed of light. Not approximately the speed of light. Exactly the speed of light. It can never slow down, never speed up. It's born moving at light speed, and it continues at that speed until it's absorbed by something. And because of special relativity, which we'll get into later, this means something absolutely mind-blowing. From the photon's perspective, if it even has a perspective, no time passes. A photon emitted from a distant star billions of light years away experiences its entire journey, from the moment it's created to the moment it hits your eye, as instantaneous. Zero elapsed time. Think about that. The photon doesn't experience the billions of years of travel. From its reference frame, it's everywhere along its path simultaneously. This is crucial for understanding why you can't touch a photon. Because touching implies a sustained interaction, an exchange of momentum over time, a period where two things are in contact, but a photon doesn't experience time. It doesn't have a rest frame. There's no reference frame in which a photon is standing still, waiting to be touched. The very concept of touching breaks down. Let me ask you something that's going to seem simple, but I promise it's not. What does it mean to touch something? Seriously, think about it for a moment. When you touch a table, what's actually happening? You might think your hand is making contact with the wood. You might think the atoms in your skin are pressing against the atoms in the table. But here's the truth that's going to change how you see everything. Your hand never actually touches the table. Not even close. Matter is almost entirely empty space. An atom is made of a nucleus surrounded by electrons, and the nucleus is about 100,000 times smaller than the atom itself. If an atom were the size of a football stadium, the nucleus would be a grape sitting at the center, and the electrons would be tiny specks orbiting near the outer walls. Everything in between is empty space. Not just empty, but emptier than the emptiest vacuum we can create in a laboratory. So when your hand approaches a table, what's actually happening at the atomic level? The electrons in your hand are negatively charged. The electrons in the table are also negatively charged. And like charges repel, as your hand gets close to the table, the electrons in your skin and the electrons in the table's surface begin to repel each other through electromagnetic force. This repulsion increases dramatically as the distance decreases. It's not a wall exactly. It's more like two magnets with the same poles facing each other. You can push them closer, but they push back harder and harder. At the atomic scale, your hand stops when the electromagnetic repulsion force equals the force you're applying. You never make contact. You're hovering above the table's surface by a distance of about a nanometer, which is billionths of a meter. What you experience as the solidity of the table, the sensation of touch, is actually this electromagnetic repulsion. The electrons in your skin are being pushed back by the electrons in the table, and your nerves interpret this as contact. But it's not contact, it's repulsion. You're feeling a force field. Everything you've ever touched in your life, you've never actually touched. You're floating through existence, separated from everything by invisibly tiny gaps, maintained by electromagnetic forces. Now, photons are carriers of the electromagnetic force. When I say that, I mean something very specific. In quantum field theory, forces between particles are mediated by the exchange of other particles called force carriers. For the electromagnetic force, the force carrier is the photon. When two electrons repel each other, they do so by exchanging virtual photons. These aren't the same as the real photons we see as light. Virtual photons are quantum fluctuations that exist for incredibly brief moments, consistent with the uncertainty principle, and they carry the electromagnetic force between charged particles. This is where things get fascinating. Every time you touch something, every time you feel that electromagnetic repulsion, you're actually interacting with virtual photons. The sensation of touch, the force that keeps you from falling through your chair, the solidity of matter itself, all of it is mediated by photons. In a very real sense, you're constantly being bombarded by photons, constantly exchanging them with everything around you. The question isn't really whether you can touch a photon. The question is whether you're doing anything other than touching photons. But there's a crucial difference between virtual photons and real photons. A real photon, a kind that carries light from the sun to your eye, is what we call on shell. It satisfies the energy-momentum relation exactly. It's a stable, independent quantum that can travel indefinitely until it interacts with matter. A virtual photon is off-shell. It doesn't satisfy the normal energy-momentum relation. It exists only in the context of an interaction between charged particles. It's more of a mathematical description of how the force works than an actual particle you could catch or observe directly. So when we ask about touching a real photon, we're asking something different. We're asking whether you can have a sustained mechanical interaction with a quantum of light. And the answer is no, but for reasons that are even stranger than you might think. Let me explain why. A photon carries momentum. Einstein showed that even though a photon has no mass, it has momentum equal to its energy, divided by the speed of light, or equivalently, Planck's constant divided by its wavelength. When a photon hits something and is absorbed, it transfers this momentum. This is called radiation pressure. It's a real measurable effect. In fact, there are proposals to use radiation pressure from sunlight to propel spacecraft with solar sails. The momentum from individual photons is tiny, but with enough photons, you can generate measurable force. So in some sense, you do interact with photons mechanically. When sunlight hits your skin, photons are transferring momentum to you. You're being pushed, ever so slightly, by the pressure of light. But this isn't what we normally mean by touching. Because the moment a photon transfers its momentum to you, it ceases to exist. The photon is absorbed. Its energy is converted into other forms, typically heat or a chemical reaction in the molecules of your skin or the light-sensitive cells in your eyes. The photon doesn't bounce off like a tennis ball. It doesn't maintain its identity. It's destroyed in the interaction. This is fundamentally different from touching a baseball. When you catch a baseball, the ball remains a ball. Atoms and molecules shift around. Kinetic energy is converted to heat and deformation, but the baseball persists as an object. A photon doesn't persist. It's all or nothing. It gives up all its energy in a single quantum leap, and it's gone. This is why catching a photon isn't like catching anything else. You can't hold it. You can only absorb it. Here's an analogy. Think of it like trying to touch a raindrop. When a raindrop hits your hand, what happens? It splashes. It ceases to be a distinct drop and becomes part of the water film on your skin. You can't touch the raindrop and have it remain a raindrop. The interaction destroys its identity. A photon is similar, but even more extreme. The moment you interact with it, it's annihilated. Its energy is transferred to electrons in atoms, which jump to higher energy levels. Later, they might fall back down and emit new photons, but those aren't the same photon. The original is gone. This is the first major mind-blown moment I want you to really sit with. Every time you see anything, every time light enters your eye, photons are being destroyed. Vision isn't passive. It's an act of annihilation. The light that left the sun 8 minutes ago, that traveled 150 million kilometers through the vacuum of space, that bounced off the page or screen you're looking at, enters your eye and is absorbed by molecules in your retina. Those photons are destroyed, their energy used to trigger a cascade of chemical reactions that your brain interprets as sight. You're not seeing light. You're experiencing the aftermath of light's destruction. Every moment of visual experience is built on the death of countless photons. Now let's go deeper. We need to talk about what a photon actually is in the quantum mechanical sense, because this is where things start to get truly bizarre. I've told you that a photon is both a wave and a particle, but what does that really mean? How can something be two seemingly contradictory things at once? The answer lies in the quantum mechanical description of reality, and it's going to challenge your intuitions in ways you might not expect. In quantum mechanics, particles aren't really particles in the classical sense. They're described by something called a wave function. The wave function is a mathematical object that contains all the information about a quantum system. For a photon, the wave function tells you the probability of finding the photon at any given location if you were to measure its position. And here's the key thing. Before you measure it, the photon doesn't have a definite position. It exists in what's called a superposition, a combination of all possible positions simultaneously, weighted by the probabilities given by the wave function. This isn't just ignorance on our part. It's not that the photon is really at some specific location, and we just don't know where. According to quantum mechanics, the photon literally doesn't have a definite position until you measure it. Before measurement, it's spread out in a wave-like pattern of probability. This probability wave can extend over a large region of space. A photon from a distant star, before it hits your eye, has a wave function that extends across thousands or even millions of kilometers. In some sense, the photon is everywhere along its path at once. And something incredible happens. When the photon is absorbed by a molecule in your retina, the wave function collapses. Suddenly, the photon is found at one specific location. All the other possibilities vanish instantly. This is called wave function collapse or measurement, and it's one of the deepest mysteries in quantum mechanics. Nobody fully understands why or how it happens. We just know that it does. The act of measurement, or more precisely, the active interaction that counts as a measurement, forces the quantum system to choose one outcome from all the possibilities. This is why the double-slit experiment is so mind-blowing. Let me describe it in detail, because it perfectly illustrates the weirdness we're dealing with. Imagine you have a light source, 2 narrow slits, and a screen. You shine light at the slits. If light were classical particles, some particles would go through the left slit and hit the screen, creating a bright area. Some would go through the right slit, creating another bright area. You'd see 2 bands of light, but that's not what happens. You see an interference pattern, many alternating bright and dark bands. This is because the light waves going through the left slit and the right slit overlap and interfere. Where they're in phase, they add up to create brightness. Where they're out of phase, they cancel out to create darkness. Okay, that makes sense if light is a wave. But here's where it gets crazy. Now dim the light way down so that only one photon passes through the apparatus at a time. You might think that each photon would go through either the left slit or the right slit, and eventually you'd build up 2 bright bands. But that's not what happens. Each photon still contributes to the interference pattern. Over time, as you send through more and more single photons, one at a time, the same interference pattern emerges. How is that possible? Each photon is alone. It's not interfering with other photons. It's as if each photon goes through both slits at once and interferes with itself. And it gets even stranger. Now put detectors at the slits to see which slit each photon goes through. When you do this, the interference pattern disappears. You get 2 bright bands, just like you'd expect for classical particles. The mere act of observing which path the photon takes changes its behavior. When you're not looking, the photon behaves like a wave and goes through both slits. When you are looking, it behaves like a particle and goes through one slit or the other. This is wave-particle duality in action. The photon's behavior depends on how you observe it. Let me give you an analogy to make this more intuitive. Think of it like a video game, where the graphics only render the parts of the world you're looking at. When you're not observing a photon's path, the universe treats it like a wave, a spread-out possibility. Only when you measure it does the universe render a specific outcome. It's not a perfect analogy, but it captures the idea that reality at the quantum level is fundamentally different from the solid, definite reality we experience in everyday life. Now, here's the connection to touching a photon. If a photon doesn't have a definite position until you measure it, and if measuring it means absorbing it and destroying it, then what does it mean to touch one? In the classical world, touching something means your hand occupies the same space as the object and forces are exchanged. But a photon doesn't occupy a definite position in space. It's spread out as a probability wave. You can't put your hand where the photon is, because the photon isn't anywhere specific until you interact with it. And the moment you do interact with it, the moment you find it at a location, it's absorbed and ceases to exist. This is fundamentally different from touching a baseball or a rock or even a molecule. Those objects are made of many particles, and while each individual particle is also described by a wave function, the collective behavior of trillions upon trillions of particles averages out to something that looks classical. A baseball has a definite position because the quantum uncertainties are negligibly small compared to the size of the ball. But a single photon is irreducibly quantum. It doesn't become classical just because you look at it. It remains a quantum object right up until the moment of interaction, at which point it vanishes. Here's a thought experiment. Imagine you had a perfect photon trap, a region of space where you could confine a photon without absorbing it. Such a thing is possible in principle. You could use mirrors to create a cavity where the photon bounces back and forth. In fact, physicists do this in experiments. They create optical cavities where photons can be trapped for relatively long times, long enough to study their properties. Even in this scenario, you still can't touch the photon in any meaningful sense. The photon is bouncing around at the speed of light, existing in a superposition of states. If you try to interact with it, to feel it, you'll absorb it. The trap can confine it, but only by never truly interacting with it, only by redirecting it with reflected electromagnetic fields. Let me tell you about an actual experiment that demonstrates just how weird photons are. In the 1980s, a French physicist named Alain Aspect performed a series of experiments testing quantum entanglement. He created pairs of photons that were entangled, meaning their properties were correlated in ways that can't be explained by classical physics. He sent these photons in opposite directions and measured their polarizations. Quantum mechanics predicts that the measurement results should be correlated in a way that violates what are called Bell's inequalities. And that's exactly what Aspect found. The photons were behaving in ways that seemed to require them to communicate with each other faster than light, or more accurately, to be connected in a way that transcends space and time. This experiment, and many others like it, confirmed that quantum mechanics is correct and that reality at the quantum level is deeply non-local. Particles that have interacted remain connected in a way we don't fully understand. And photons, being the quantum objects they are, participate fully in this weirdness. When you think about touching a photon, you're not just thinking about touching a little ball of light. You're thinking about interacting with an object that defies classical description, that exists in multiple states simultaneously, that doesn't have definite properties until measured, and that's potentially entangled with other photons across the universe. This is the second mind-blown moment. Photons aren't little balls of light traveling through space. They're ripples in the electromagnetic field, described by probability waves, existing in superpositions of all possible states until the moment of observation collapses them into a single outcome. And that moment of observation, that collapse, is the destruction of the photon. You can't touch a photon because touching implies a sustained interaction with something that has a definite position. A photon has neither. Let's take this further. I want to talk about what happens from the photon's perspective, which is a phrase that doesn't really make sense. But bear with me because it's going to reveal something profound about the nature of time and space. According to Einstein's theory of special relativity, time passes differently depending on how fast you're moving. This is called time dilation. The faster you move, the slower time passes for you relative to someone who's stationary. At everyday speeds, this effect is negligibly small. But as you approach the speed of light, it becomes dramatic. Here's the formula that describes it. If you're moving at velocity v, time for you passes more slowly by a factor of the square root of 1v squared per c squared, where c is the speed of light. When you're stationary, v is 0, and this factor is 1. Time passes normally. As v increases, this factor decreases, meaning time passes more slowly. When v equals c, when you're moving at the speed of light, this factor becomes 0. Time stops. For a photon, which always moves at the speed of light, time doesn't pass at all. From the moment a photon is created to the moment it's destroyed, zero time elapses in its reference frame. Now, technically, we can't talk about the photon's reference frame because special relativity breaks down at the speed of light. There's no valid reference frame moving at light speed. But we can take a limit, imagine traveling faster and faster, approaching the speed of light, and see what happens. In that limit, time dilation becomes infinite. A journey that takes billions of years in Earth's reference frame happens instantaneously in the photon's reference frame. Think about the implications of this. A photon emitted from a galaxy billions of light years away travels for billions of years from our perspective. From the photon's perspective, if we could speak of such a thing, the journey is instantaneous. The photon's creation and destruction happen at the same moment. It doesn't experience the vast emptiness of intergalactic space. It doesn't age. It doesn't change. From its point of view, the entire universe along its path is compressed to a single point. There's another weird effect called length contraction. Just as time slows down at high speeds, lengths contract in the direction of motion. An object moving at velocity v is shortened by that same factor, the square root of 1 v squared per c squared. For a photon, this factor is 0. Distances in the direction of travel are contracted to nothing. From the photon's perspective, the entire distance it travels, whether it's a meter or a billion light years, is 0. The starting point and the ending point are at the same location. Combine these two effects, time dilation and length contraction, and you get something utterly bizarre. For a photon, the universe is a single point in space and a single instant in time. There's no journey. There's no duration. There's just creation and destruction, emission and absorption, a single timeless event. The photon doesn't exist in time as we understand it. It connects 2 points in space-time, the event of its emission and the event of its absorption, but it doesn't experience anything between them because, from its perspective, there is no between. This is why the question of touching a photon is so strange. Touching implies duration. It implies that for some period of time, two things are in contact. But a photon doesn't have duration in its own reference frame. And while it's traveling from our reference frame, it's moving at the speed of light. You can't catch up to it. You can't match its speed because anything with mass requires infinite energy to accelerate to the speed of light. You can only wait for the photon to arrive, and when it does, it's absorbed instantly. There's no moment of contact. There's only before the photon arrives and after it's been absorbed. Let me share an analogy that might help. Think of a photon like a message in a bottle thrown into a river. From the perspective of someone on the shore, the bottle floats downstream, traveling from the person who threw it to the person who retrieves it. The journey takes time. But imagine if, from the bottle's perspective, the entire river was compressed to a single point. The moment of being thrown and the moment of being caught happen simultaneously. There's no journey from the bottle's perspective, only a connection between thrower and catcher. A photon is like that, but even more extreme because the compression is total. The photon is the connection itself, not an object traveling through space. This has profound implications for causality and the structure of spacetime. In relativity, we describe events using something called a light cone. If an event happens at a particular place in time, the light cone represents all the places and times that could be causally connected to that event. Anything inside your past light cone could have influenced you because light, or anything traveling slower than light, could have reached you from there. Anything inside your future light cone can be influenced by you because you can send light or information there. Photons travel along the surface of the light cone. They're the boundary of causality. They connect events that are at the maximum possible separation in spacetime, while still being able to influence each other. When you see a star, you're receiving photons that traveled from the star to you. Those photons are connecting your retina right now to the surface of that star, years or centuries or millennia ago. depending on the distance. The photon has linked two events in spacetime: the emission of the photon from an excited atom in the star, and the absorption of the photon by a molecule in your eye. From the photon's perspective, these are the same event. From your perspective, they're separated by vast distances and times. The photon bridges that gap, not by traveling through it, but by connecting the endpoints directly. Here's another mind-blowing fact. Because photons don't experience time, they don't decay. Particles with mass can be unstable. A free neutron, for example, will decay at about 15 minutes on average into a proton, an electron, and a neutrino. But a photon, once created, lasts forever unless it interacts with something. The oldest photons in the universe, when a photon enters your eye, it passes through the cornea and lens, which focus it onto the retina. The retina is lined with specialized cells called photoreceptors, rods and cones. These cells contain molecules called photopigments. In rods, the photopigment is rhodopsin. Rhodopsin consists of a protein called opsin and a light-sensitive molecule called retinal. Retinal is derived from vitamin A, which is why vitamin A deficiency can cause vision problems. In its resting state, retinal has a kinked shape. When a photon is absorbed, its energy causes retinal to change shape, straightening out. This is called photosonorization. This shape change in retinal triggers a cascade of events. The straightened retinal activates the opsin protein, which in turn activates a signaling molecule called transducin. Transducin activates an enzyme that breaks down a molecule called cGMP. Decrease in cGMP causes ion channels in the photoreceptor cell membrane to close. This changes the electrical potential of the cell, generating an electrical signal. This signal is passed to other neurons in the retina, which process the information and send it through the optic nerve to the brain. Your brain interprets these electrical signals as vision. All of this entire cascade of chemical and electrical events that allows you to see, is triggered by a single photon. One quantum of light, carrying a tiny amount of energy, can cause retinal to change shape, which sets off a chain reaction that ultimately results in you perceiving light. This is quantum mechanics directly affecting your conscious experience. The absorption of a single photon, a purely quantum event, has macroscopic consequences. You become aware that you saw something. Here's what's amazing about this. Your eyes are remarkably sensitive. Under ideal conditions, a rod cell can detect a single photon. In experiments, people have reported seeing flashes of light that correspond to just a few photons hitting their retina. This is at the absolute limit of what's physically possible. You can't detect half a photon or a quarter of a photon. The photon is the quantum, the indivisible unit of light. Your eyes are quantum detectors, sensitive to the smallest possible amount of light. But let's think about what's actually happening here. The photon is absorbed by the retinal molecule. The photon's energy, which for visible light is around 2 to 3 electron volts, is transferred to the molecule. This energy is exactly what's needed to change the shape of retinal from its kinked form to its straight form. If the photon had too little energy, the transition wouldn't happen. If it had too much energy, the excess would be dissipated as heat. The process is exquisitely tuned. Evolution has crafted molecules that are perfectly sensitive to the energies of visible light photons. Once the photon is absorbed, it no longer exists. Its energy has been transferred to the retinal molecule. That energy is now embodied in the new shape of the molecule, in the strain of the chemical bonds that have been rearranged. Later, through a series of biochemical steps, the retinal will be returned to its original kinked shape, ready to absorb another photon. But that original photon is gone. It's been converted into molecular motion, into chemical energy, into electrical signals. The photon's identity has been erased. In its place is information, the fact that a photon arrived at a particular location on your retina at a particular time. This is the nature of all photon interactions. When a photon is absorbed, it ceases to exist as a photon. Its energy is transferred to whatever absorbed it. This energy might raise an electron to a higher energy level in an atom, creating what's called an excited state. That electron might later fall back down, emitting a new photon, but it's not the same photon. It's a different quantum, born from the energy released when the electron drops. Photons are constantly being created and destroyed throughout the universe. They're not conserved like matter. They pop into existence whenever charged particles accelerate or when excited atoms relax. They vanish whenever they're absorbed. Let me tell you about a specific experiment that demonstrates the quantum nature of photon absorption. It's called the photoelectric effect, the same phenomenon Einstein explained to win his Nobel Prize. When you shine light on a metal surface, electrons are ejected from the surface. These are called photoelectrons. Now, if light were a continuous wave, you'd expect that brighter light would always eject electrons with more energy, because more energy is being delivered to the surface. But that's not what happens. The energy of the photoelectrons depends only on the frequency of the light, not its intensity. Brighter light produces more photoelectrons, but each individual electron has the same energy, determined by the frequency of the light. This makes perfect sense if light comes in photon packets. Each photon has an energy proportional to its frequency. E equals hf, where h is Planck's constant and f is frequency. When a photon hits the metal, it can transfer all of its energy to a single electron. If that energy is greater than the work function of the metal, the minimum energy needed to free an electron, the electron is ejected. The kinetic energy of the ejected electron is the photon's energy minus the work function. Higher frequency means higher photon energy, which means more energetic photoelectrons. Higher intensity means more photons, which means more photoelectrons, but not more energy per electron. This is a direct demonstration that light is quantized, that it comes in discrete packets that interact with matter one quantum at a time. And it shows that the interaction is immediate and total. The photon doesn't gradually give up its energy. It transfers all its energy at once in a single quantum leap and disappears. Here's the fourth major mind-blown moment. Every time you see anything, you're experiencing the results of quantum measurement at the most fundamental level. Single photons, traveling for perhaps billions of years, enter your eye and are annihilated by molecules in your retina. Their energy triggers chemical changes that result in electrical signals that your brain interprets as the sight of a star, a face, a tree, words on a screen. Vision is a quantum phenomenon. Consciousness, at least in the sense of visual awareness, is built on the foundation of individual quantum events. You are a quantum observer. Collapsing wave functions billions of times per second just by looking at the world around you. Let's explore one of the strangest aspects of photons, their relationship with vacuum and virtual particles. You might think of empty space, a vacuum, as being truly empty. Nothing there, just void. But in quantum mechanics, there's no such thing as truly empty space. The vacuum is seething with activity, with quantum fluctuations. These fluctuations arise from the Heisenberg uncertainty principle, which states that you can't simultaneously know both the exact energy and the exact time at which that energy is measured. For very short periods of time, energy can fluctuate, and these fluctuations manifest as virtual particle-antiparticle pairs popping into existence and then annihilating each other. For the electromagnetic field, these are virtual photons. They appear and disappear constantly, everywhere in space. You might wonder how this is possible, how energy can just appear from nothing. The answer is that it's only possible for incredibly brief moments. The more energy borrowed, the shorter the time it can exist. According to the relation delta E times delta T is greater than or equal to A2, where A is the reduced Planck constant. These virtual photons exist for times so short that they can't be directly observed without disrupting the system, but they have real, measurable effects. One of the most famous effects of virtual photons is the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. If you place two uncharged, parallel metal plates very close together in a vacuum, they'll attract each other. Why? Because the space between the plates can only support certain wavelengths of virtual photons, those that fit exactly between the plates. Outside the plates, all wavelengths are possible. This means there's a higher density of virtual photons outside than inside, which creates a net pressure pushing the plates together. The Casimir force has been measured experimentally and matches the predictions of quantum field theory precisely. This is astonishing. Virtual particles that don't really exist in the classical sense, that are more like mathematical descriptions of quantum fluctuations, nonetheless produce measurable forces. The vacuum isn't empty. It's a roiling sea of virtual particles, constantly appearing and disappearing. And photons, both real and virtual, are central to this picture. The electromagnetic field permeates all of space, and its quantum fluctuations are what we call virtual photons. Now, here's where it connects to the question of touching a photon. When two charged particles interact, say two electrons repelling each other, quantum field theory describes this interaction as the exchange of virtual photons. One electron emits a virtual photon, which is absorbed by the other electron. This exchange carries momentum and energy, which manifests as the electromagnetic force between them. The virtual photon is the force. In a very real sense, all electromagnetic interactions, including the forces that prevent your hand from passing through a table, are mediated by photons. So when you try to touch something, when electromagnetic repulsion prevents contact, you're interacting with virtual photons. This is the mechanism by which the force is transmitted. You can't observe these virtual photons directly because they exist only within the context of the interaction. They're not on-shell real photons that could travel independently, but they're there, carrying the force, mediating the interaction. In quantum field theory, forces aren't action at a distance. They're the result of particle exchange. This raises a fascinating question. Are virtual photons and real photons the same kind of thing? Or are they fundamentally different? The answer is subtle. They're described by the same quantum field, the electromagnetic field. A real photon is an excitation of this field that satisfies certain conditions, namely that it's on shell, that its energy-momentum relation is satisfied exactly. A virtual photon is an excitation that doesn't satisfy these conditions. It's off shell. It's a quantum fluctuation, a temporary borrowing of energy from the vacuum. But the distinction isn't absolute. Under certain conditions, virtual photons can become real photons. For example, in a very strong electric field, such as near a black hole or in certain particle collisions, a virtual photon pair from the vacuum can be pulled apart and made real. This is related to a phenomenon called Hawking radiation, predicted by Stephen Hawking in 1974. Near the event horizon of a black hole, quantum fluctuations can create particle-antiparticle pairs. If one falls into the black hole and the other escapes, the escaping particle becomes real, carrying away energy. The black hole evaporates, losing mass due to this quantum effect. The vacuum fluctuations have been converted into real particles, including real photons. Here's another incredible example. In extremely intense laser fields, physicists have predicted that the vacuum itself can be torn apart, converting virtual photon pairs into real electron-positron pairs. This is called Schwinger pair production, named after physicist Julian Schwinger, who predicted it in 1951. It requires field strengths far beyond what we can currently achieve, but future laser facilities might make it possible. The vacuum would literally spark into existence with real particles, created from the energy of the light field interacting with the quantum fluctuations of the vacuum. This is the fifth mind-blown moment. The vacuum isn't empty. It's filled with virtual photons, quantum fluctuations of the electromagnetic field. Every force you experience, every solid surface, every sensation of touch is mediated by these virtual photons. They're not quite real, not quite unreal. They're quantum entities that exist in the fuzzy boundary between existence and non-existence, and they're essential to the structure of reality. When you ask whether you can touch a photon, the answer is that you're already touching virtual photons constantly. They're the mechanism of touch itself. But real photons, the ones that carry light, are different. They're independent quanta that can't be touched without being destroyed. Let's talk about something even weirder: the path that a photon takes from one place to another. You might think that a photon travels in a straight line, the shortest path from its source to its destination. After all, light rays in classical optics are straight lines unless they're bent by refraction or reflection. But in quantum mechanics, the picture is far stranger. According to quantum field theory, specifically the approach developed by Richard Feynman called the path integral formulation, a photon doesn't take a single path. It takes all possible paths simultaneously. Imagine a photon emitted from a light source and absorbed by a detector. There's the straight line path, but there are also paths where the photon curves upward or downward or spirals, or takes a detour through Jupiter and back. Every conceivable path, no matter how absurd, contributes to the photon's wave function. Each path has an associated probability amplitude, a complex number that describes the likelihood and phase of that path. To find the total probability amplitude for the photon to reach the detector, you add up the amplitudes for all possible paths. This is called a path integral. Now, here's the key insight. Most of these crazy paths cancel each other out due to destructive interference. Paths that are wildly different have very different phases, and when you add them up, they tend to cancel. The paths that contribute most are those near the classical path, the straight line or the path predicted by classical optics, because these paths have similar phases and add up constructively. This is why classical optics works. It's the limit of quantum mechanics, where the effects of all the crazy paths average out. But the crazy paths are still there. They still contribute to the wave function. And in certain situations, they become important. For example, in the double-slit experiment, the photon is taking paths through both slits simultaneously. The interference pattern arises from the fact that paths through the left slit and paths through the right slit have different phases, and when you add them up, you get constructive and destructive interference. The photon is literally exploring all possible routes, and the pattern you see on the screen is the result of summing over all these routes. This is Feynman's path integral formulation, and it's one of the most beautiful and strange ideas in physics. It says that quantum particles don't follow a single trajectory. They explore all possible trajectories at once, and the one you observe is the result of quantum interference between all these possibilities. Feynman developed this approach in the 1940s, and it's now the foundation of quantum field theory, the most accurate description of fundamental physics we have. Let me give you an analogy. Imagine you want to get from your home to a friend's house. In classical physics, you'd take a specific route, probably the fastest or most convenient. But in the quantum world, it's as if you simultaneously take every possible route: the highway, the back roads, through the park, around the world the long way, even routes that loop back on themselves multiple times. Each route has a probability amplitude, and when you arrive, the likelihood of finding you there is determined by summing all these amplitudes. Most routes cancel out, but the efficient ones reinforce each other, so you're most likely to be found having taken a sensible route. But there's still a tiny probability that you took an absurd route, and that contributes to the overall picture. For a photon, this means it doesn't have a well-defined trajectory. You can't say it went from A to B along a specific path. It went along all paths, and the path you observe, if you observe it, is the result of the wave function collapsing due to your observation. Before observation, the photon is in a superposition of being along all paths simultaneously. This is another reason why touching a photon is so strange. If the photon doesn't have a definite path, how can you intercept it? You can't position yourself to catch something that's everywhere at once, along all possible routes. Here's an experiment that demonstrates this. In quantum optics, researchers have done experiments with single photons where they can control the paths the photon can take. Using beam splitters and mirrors, they create situations where a photon could go one way or another way, or both ways. They find that the photon behaves as if it's going both ways simultaneously, interfering with itself, even though it's a single photon. If they measure which path it took, the interference disappears. The act of measurement forces the photon to choose a path, but before measurement, this isn't time travel in the science fiction sense. It's a consequence of the fact that, in quantum mechanics, a path isn't fixed until it's observed. The photon's path is indeterminate until the measurement is made, even if that measurement comes after the photon has supposedly already traveled. This challenges our deepest intuitions about causality and the flow of time. It suggests that the past, present, and future are entangled in ways we don't fully understand. This is the sixth major revelation. A photon doesn't travel along a single path. It travels along all possible paths simultaneously. And what you observe is the result of quantum interference between these paths. The photon's trajectory is fundamentally indeterminate until observed. This means that a photon isn't a little ball following a specific route through space. It's a quantum probability amplitude spread over all possible routes, all possible histories, and it only collapses into a specific outcome when observed. You can't touch a photon in flight because it's not in flight in any classical sense. It's everywhere and nowhere, exploring all possible futures until you force it to choose one. Now let's connect all of this to special relativity more explicitly. I mentioned earlier that photons don't experience time, but I want to dive deeper into what this means for the structure of spacetime. Special relativity, Einstein's theory from 1905, revolutionized our understanding of space and time. Before Einstein, people thought of space and time as separate, absolute things. There was a universal now, a moment in time that was the same for everyone in the universe. Einstein showed that this is wrong. Space and time are interwoven into a single fabric called spacetime, and different observers can disagree about whether two events happened at the same time or in what order they happened. The key insight is that the speed of light is the same for all observers, regardless of how they're moving. This is the principle of the constancy of the speed of light. If you're on a train moving at half the speed of light and you shine a flashlight forward, the light doesn't move at 1.5 times the speed of light relative to the ground. It moves at exactly the speed of light, c, relative to both you and someone standing on the ground. This seems impossible, but it's a consequence of the fact that space and time adjust to keep the speed of light constant. To make this work, time must be relative. Clocks moving relative to each other tick at different rates. This is time dilation, which we've already discussed. And distances must be relative. Lengths contract in the direction of motion. These aren't illusions or measurement artifacts. They're real changes in the geometry of spacetime. Two observers moving relative to each other genuinely experience different durations and distances. Now, for a photon, which moves at the speed of light, these effects become extreme. Time dilation becomes infinite. Length contraction becomes total. From the photon's perspective, if such a perspective could exist, the universe is a single point in space and a single instant in time. The photon's world line, its path through spacetime, is what we call null or light-like. It connects events that are separated by a distance in space exactly equal to the distance in time when measured in units, where the speed of light is 1. This is the boundary of causality. Events separated by light-like intervals can just barely influence each other, with a signal traveling at the speed of light. Here's a fascinating consequence. In space-time diagrams, where we plot space on one axis and time on another, massive particles follow world lines that are tilted relative to the time axis. They move through space as time passes. The faster they move, the more their world line tilts toward the spatial axis. At the speed of light, the world line tilts exactly 45 degrees, again in units where c equals 1. This is the light cone. Nothing can tilt more than 45 degrees without exceeding the speed of light, which is impossible for anything with mass. A photon's world line lies right on the light cone. It's moving as fast as it's possible to move. And from the photon's perspective, its world line is collapsed to a single point. The spatial and temporal separation between emission and absorption is 0. This is why photons are so special. They're the speed limit of the universe. They're the connection between causally connected events. They're the fabric of causality itself. Let me tell you about something called the twin paradox, which illustrates time dilation in a dramatic way. Imagine two twins. One stays on Earth. The other gets on a spaceship, travels to a distant star at a speed close to the speed of light, turns around, and comes back. When the traveling twin returns, they've aged less than the twin who stayed home. This isn't a trick or an illusion. The traveling twin has literally experienced less time. If they traveled fast enough and far enough, the difference could be decades or even centuries. The stay-at-home twin could be dead of old age while the traveling twin is still young. Now imagine taking this to the extreme. The traveling twin moves at speeds closer and closer to the speed of light. In the limit, approaching light speed, the traveling twin ages hardly at all, no matter how long the journey takes from Earth's perspective. At exactly the speed of light, which is impossible for the twin, but possible for a photon, 0 time passes for the traveler. A photon is the ultimate time traveler, jumping from its creation to its destruction without experiencing any duration in between. This has implications for how we understand photons. They're not objects that persist through time. They're more like connections, bridges, instantaneous links between two events in spacetime. When a photon is emitted from a star and absorbed by your eye, those two events are connected by the photon's world line. From your perspective, the photon traveled for years. From the photon's perspective, it didn't travel at all. It simply connects the star's past to your present. Here's the seventh mind-blown moment. Photons are the threads that weave together the causal structure of the universe. They connect events across space and time, and from their own perspective, they don't experience that space and time at all. They're timeless, eternal in the sense that they don't age, yet ephemeral in that they exist only in the act of connecting emission to absorption. When you ask whether you can touch a photon, you're asking whether you can grasp one of these threads, one of these causal connections. And the answer is no, because the photon doesn't exist in the way objects exist. It's not a thing that occupies space and persists through time. It's an event, a quantum of action, a connection between causes and effects. Let's now explore some of the cutting-edge experiments and technologies that involve manipulating photons. Because even though you can't touch a photon in a classical sense, physicists have developed incredible techniques for controlling, trapping, storing, and entangling photons. These experiments reveal even more about the strange nature of light and push the boundaries of what's possible with quantum mechanics. One of the most remarkable achievements is quantum teleportation. This isn't science fiction teleportation, where an object disappears and reappears somewhere else. It's a process where the quantum state of a particle is transferred to another particle at a distant location, without the two particles ever traveling the distance between them. In 1993, physicists proposed a protocol for quantum teleportation using entangled photons, and in 1997, Anton Zeilinger's group in Austria performed the first experimental demonstration. Here's how it works. You start with two photons that are entangled, meaning their quantum states are correlated. One photon stays with Alice, the other is sent to Bob, far away. Alice has a third photon, whose state she wants to teleport to Bob. She performs a special measurement on her original photon and the photon to be teleported. This measurement produces two classical bits of information, which she sends to Bob through a normal communication channel. Bob uses these two bits to perform an operation on his entangled photon, and voila, his photon now has the state that Alice's third photon had. The original photon's state is destroyed in the process, as required by the no-cloning theorem of quantum mechanics, which says you can't make perfect copies of unknown quantum states. This is astonishing. The quantum state has been transferred without traveling through the space in between. The information has jumped, so to speak, from Alice's location to Bob's, carried not by the photons themselves, but by the entanglement that connects them. And photons are perfect for this, because they can be easily entangled, transmitted over long distances through optical fibers or free space, and manipulated with high precision using mirrors, beam splitters, and detectors. Quantum teleportation has been demonstrated over increasingly large distances. In 2012, Zeilinger's group teleported quantum states between two islands in the Canary Islands, 143 kilometers apart. In 2017, Chinese scientists used a satellite called MISHIS to teleport quantum states from Tibet to a satellite in orbit, 1,400 kilometers away. These experiments are paving the way for quantum communication networks, where information is sent securely using the principles of quantum mechanics. Another incredible technology is quantum computing. While most quantum computer architectures use superconducting circuits or trapped ions as qubits, there are also photonic quantum computers that use photons as qubits. The quantum state of a photon can encode information, for example in its polarization or in which path it takes through an interferometer. Photons have advantages. They don't interact strongly with the environment, which reduces errors, and they can travel long distances, which is useful for connecting different parts of a quantum network. In 2020, a team from the University of Science and Technology of China announced a photonic quantum computer called Jiuzhang. They claimed it achieved quantum advantage, performing a specific calculation faster than any classical computer could. The calculation involved sampling from a complex probability distribution, a task that's hard for classical computers, but natural for quantum systems. Jiuzhang used 76 photons and a complex network of beam splitters and detectors to perform this calculation. While the practical applications are still unclear, it demonstrates that photons can be harnessed for quantum information processing. Let me tell you about another mind-bending experiment, quantum erasure. This is a variation of the double-slit experiment that shows just how strange quantum mechanics is. Remember, in the double-slit experiment, if you measure which slit the photon goes through, the interference pattern disappears. The active measurement forces the photon to behave like a particle. But what if you could erase the information about which path the photon took after the photon has already passed the slits, but before it hits the screen? Does the interference pattern come back? Amazingly, yes. In a quantum eraser experiment, you set up the system so that you can, in principle, determine which slit the photon went through, but you don't actually look at that information. Instead, you erase it, making it impossible to determine the path, even in principle. When you do this, the interference pattern reappears. The photon behaves as if it went through both slits, even though the path information was, briefly, in principle available. The interference depends not on what you know, but on what can be known. If the information exists, even if no one looks at it, the interference is destroyed. If the information is erased, the interference returns. This has been extended to something called delayed choice quantum erasure, which I mentioned earlier. In these experiments, the decision to erase the path information is made after the photon has already hit the screen. Classical intuition says this shouldn't matter. The photon already hit the screen. It should have already either made an interference pattern or not. But the results show that your future decision to erase or not erase the information affects the pattern that appears on the screen. It's as if the photon's behavior retroactively adjusts based on future measurements. Now, before you start thinking this allows for time travel or sending information into the past, it doesn't. The full interference pattern only becomes apparent when you correlate this measurements at the screen with the information about whether the path information was erased. Without that correlation, you just see a random distribution of photon hits. So you can't send a signal backwards in time. But it does show that the quantum world doesn't respect our intuitive notion of past, present, and future as distinct, unchangeable categories. Here's the eighth mind-blown moment. We can manipulate photons in ways that seem to defy common sense. We can teleport their quantum states across vast distances. We can entangle them so that measuring one instantaneously affects the other, regardless of the distance between them. We can erase information about their paths and watch interference patterns appear or disappear retroactively. Photons are not just particles of light. They're tools for exploring the deepest mysteries of quantum mechanics and the nature of reality itself. And every time we perform these experiments, we're not touching photons in the classical sense, but we're interacting with them in ways that reveal their fundamentally quantum nature. Let's explore what happens when photons interact with matter on a deeper level. We've talked about absorption, but there are other types of interactions: reflection, refraction, scattering. Each of these reveals something important about the nature of light and matter. And in each case, the quantum nature of photons plays a crucial role. When a photon hits a mirror, it's reflected. Classically, we say the light bounces off. But what's really happening? At the atomic level, the photon is absorbed by electrons in the metal surface of the mirror. These electrons are then re-emitted, creating a new photon going in a different direction. The original photon is destroyed, and a new one is created. It's not a bounce in the sense of a ball bouncing off a wall. It's an annihilation and recreation event. The new photon typically has the same energy as the original, which is why mirrors don't change the color of light, but it's a different photon. You might think this is just semantics, but there are situations where it matters. For example, when a photon reflects off a moving mirror, the reflected photon's frequency can change due to the Doppler effect. This is used in techniques like laser Doppler velocimetry to measure the speed of moving objects. The interaction involves the detailed quantum mechanics of how photons couple to the electrons in the mirror, which are themselves quantum objects. Refraction, the bending of light as it passes from one medium to another, is also a quantum phenomenon at its core. When light enters water or glass, it slows down. Or rather, its phase velocity decreases. The photons still move at the speed of light, but they're constantly being absorbed and re-emitted by the atoms in the material. This process takes time, which effectively slows the propagation of the light wave through the material. The light also bends because the phase velocity changes, which is described by Snell's law. But here's a subtlety. The photons in the material aren't the same as photons in vacuum. They're what we call polaritons, hybrid excitations that are part photon and part material excitation. When a photon enters a material, it couples to the electrons in the atoms, creating these polaritons. The polaritons have different properties from bare photons. They have an effective mass, for instance, which bare photons don't have. When the light exits the material, the polaritons convert back into photons. This is a quantum mechanical process described by quantum electrodynamics, QED, the theory of how light and matter interact. Scattering is another important process. When light hits a small particle or an atom, it can be scattered in various directions. There are different types of scattering. Rayleigh scattering, which is why the sky is blue, happens when light scatters off particles much smaller than its wavelength. Blue light, with its shorter wavelength, scatters more than red light. So when sunlight passes through the atmosphere, more blue light is scattered toward our eyes. Rayleigh scattering is an elastic process, meaning the photon's energy doesn't change. It's absorbed and re-emitted with the same frequency, just in a different direction. Then there's Raman scattering, discovered by Indian physicist C.V. Raman in 1928, for which he won the Nobel Prize. In Raman scattering, the photon's energy does change. It can either gain energy from the molecule it scatters off, anti-Stokes scattering, or lose energy to the molecule, Stokes scattering. This happens because the molecule is left in a different vibrational or rotational state after the interaction. Raman scattering is a powerful tool in chemistry and materials science because it allows scientists to probe the vibrational modes of molecules, giving information about their structure and composition. There's also Compton scattering, where a photon scatters off a free or loosely bound electron. This was discovered by Arthur Compton in 1923, another Nobel Prize-winning discovery. In Compton scattering, the photon transfers some of its energy to the electron, so the scattered photon has lower energy and longer wavelength than the incident photon. This can only be explained if the photon has particle-like properties, carrying momentum and energy. Compton scattering was one of the key pieces of evidence that convinced physicists that light really does come in discrete quanta. All of these processes, reflection, refraction, scattering, involve the absorption and emission of photons. And in each case, the photon is destroyed and recreated. The identity of the photon isn't preserved. This is fundamentally different from classical particles like billiard balls, which maintain their identity when they bounce or scatter. Photons are fungible, indistinguishable. One photon of a given energy is exactly like any other photon of that energy. You can't label them or track an individual photon through multiple interactions. It's always being annihilated and recreated. This brings us to a deep question. What is the identity of a photon? In classical physics, objects have identity. This ball is that ball. But in quantum mechanics, identical particles are truly indistinguishable. There's no way, even in principle, to tell one electron from another or one photon from another. They're not just similar, they're exactly the same. This has profound consequences. It leads to quantum statistics, Bose-Einstein statistics for bosons like photons, and Fermi-Dirac statistics for fermions like electrons. Photons are bosons, which means they like to be in the same state. Multiple photons can occupy the exact same quantum state, unlike fermions, which obey the Pauli exclusion principle and can't be in the same state. This is why lasers work. A laser produces coherent light, where all the photons are in the same state, same frequency, same direction. This is achieved through a process called stimulated emission. An excited atom, when it encounters a photon, is more likely to emit a photon that's identical to the one it encountered. This creates an avalanche of identical photons, all marching in step. The result is a powerful, coherent beam of light. Bose-Einstein statistics also leads to something called the photon bunching effect. If you have a light source emitting photons randomly, you'd expect the photons to arrive at a detector independently. But because photons are bosons, they have a tendency to arrive in bunches. If one photon arrives, it's slightly more likely that another will arrive shortly after. This is a purely quantum statistical effect, and it's been measured experimentally. It's another piece of evidence that photons aren't classical particles following independent trajectories. Here's the ninth major revelation. Photons don't have persistent identity. When they interact with matter, they're annihilated and recreated. They're indistinguishable from one another. They follow Bose-Einstein statistics, which leads to phenomena like laser coherence and photon bunching. When you try to touch a photon, you're trying to interact with something that doesn't maintain a persistent identity through interactions. It's constantly being created and destroyed, a fleeting quantum excitation of the electromagnetic field. The photon is not a thing. It's a process, an event, a momentary condensation of energy into a discrete packet that dissipates the moment it interacts. Now, I want to talk about one of the most profound and controversial aspects of quantum mechanics, the measurement problem and the role of the observer. This is deeply connected to the question of touching a photon because it gets at the heart of what it means for a quantum system to interact with something macroscopic like you. When you observe a photon, when it enters your eye and triggers a chemical reaction in your retina, what exactly is happening? Is the photon's wave function collapsing? What role does consciousness play, if any? The measurement problem is this. Quantum mechanics describes systems in terms of wave functions, which evolve smoothly and deterministically according to the Schrödinger equation. But when you measure a quantum system, something different happens. The wave function collapses to one of the possible outcomes, and which outcome you get is fundamentally random, determined only by probabilities. This collapse seems to be a different type of process from the smooth evolution described by the Schrödinger equation. So why does measurement cause collapse? What counts as a measurement? Does it require a conscious observer, or is any interaction sufficient? These questions have been debated since the early days of quantum mechanics. Niels Bohr and the Copenhagen interpretation said that the wave function collapse is simply a fact of nature, and we shouldn't try to look deeper. The wave function is just a tool for predicting measurement outcomes, not a description of an underlying reality. When you measure, you get a result, and that's that. Many physicists adopted this pragmatic view, and it works perfectly well for making predictions. But it doesn't really answer the question of what's happening. Others, like Albert Einstein, were deeply uncomfortable with this. Einstein famously said, "God does not play dice," expressing his belief that quantum randomness couldn't be the final word. He thought there must be hidden variables, deeper underlying factors that determine outcomes in a way that appears random to us, but is actually deterministic. In the 1960s, physicist John Bell proved a theorem that showed any hidden variable theory would have to be non-local, meaning it would involve faster-than-light influences. Experiments testing Bell's theorem, like the ones by Alling Aspect I mentioned earlier, have confirmed that nature really is non-local in the way quantum mechanics predicts. There are no simple hidden variables that restore determinism. Another interpretation is the many worlds interpretation, proposed by Hugh Everett in 1957. In this view, the wave function never collapses. Instead, every possible outcome of a measurement actually happens, but in different branches of reality. When you measure a photon's position and find it at location A, there's another version of you in another branch who finds it at location B. All possible outcomes occur, and the universe splits into multiple branches. This avoids the measurement problem by denying that collapse happens at all, but it introduces the bizarre idea that reality is constantly branching into countless parallel universes. Then there's the idea that consciousness causes collapse. This was explored by physicists like Eugene Wigner and later popularized in various forms. The idea is that the wave function represents potentiality, and conscious observation actualizes one outcome. Your awareness somehow selects which possibility becomes real. This is appealing in some ways because it gives consciousness a fundamental role in physics, but it raises huge questions. What counts as conscious? Does a cat count? A bacterium? A computer? And how exactly does consciousness, which seems to be a property of brains made of atoms following physical laws, cause a physical process like wave function collapse? Most physicists today don't think consciousness is necessary for collapse. Instead, They favor an idea called decoherence. Decoherence happens when a quantum system interacts with its environment in a way that causes the different possible outcomes to become uncorrelated, effectively destroying the quantum superposition. The system doesn't truly collapse to one outcome, but from any practical perspective, it behaves as if it has. The different outcomes no longer interfere with each other. They've decarred into separate, classical-looking possibilities. For a photon entering your eye, decoherence happens extremely quickly. The photon interacts with molecules in your retina, which are in turn interacting with countless other molecules. The quantum information spreads out into the environment, and the superposition is lost. From your perspective, the photon is found at a specific location, but really, the quantum state has become entangled with the environment in a way that makes the superposition unobservable. Decoherence doesn't fully solve the measurement problem because it doesn't tell us which outcome actually occurs. It just explains why superpositions become unobservable in macroscopic systems. But it does show that you don't need a conscious observer. Any sufficiently complex interaction with the environment causes decoherence. A photon hitting a grain of dust in space, with no one around to observe it, still interacts in a way that localizes it, causes its wave function to effectively collapse through decoherence. So what does this mean for touching a photon? It means that the moment you interact with a photon, the moment it enters the realm of macroscopic, classical objects like your hand or your eye, decoherence kicks in. The photon's quantum superposition, its wave-like spread over all possible paths, collapses or decoheres into a classical outcome. The photon is absorbed at a specific location, but this isn't really touching in the classical sense. It's a quantum measurement event, an interaction that destroys the quantum nature of the photon and extracts classical information from it. Here's the 10th mind-blown moment. The act of observation, or more precisely, the act of interaction that constitutes measurement, is what forces quantum possibilities to become classical realities. When you try to touch a photon, you're performing a measurement. The photon's wave function decoheres due to its interaction with your macroscopic body. One outcome is realized. The photon is absorbed at a particular location. But which outcome occurs is fundamentally random, determined only by quantum probabilities. And once it occurs, the photon is gone, its energy transferred to your molecules. You haven't touched a persistent object. You've participated in a quantum measurement event that crystallized one possibility out of many and destroyed the photon in the process. In a very real sense, you're not observing reality. You're creating it through your interactions. Every measurement, every observation, every touch is an act of creation, selecting one outcome from a quantum superposition of possibilities. Let me take you deeper into the philosophical implications of all this. What does it mean that reality at its most fundamental level is made of things like photons, which don't behave like classical objects? What does it mean that particles can be in superpositions, exist in multiple states simultaneously, and only become definite when observed? This challenges some of our most basic assumptions about the nature of reality, about what it means for something to exist. One of the key philosophical questions is realism versus anti-realism. Realism is the view that physical objects have definite properties independent of observation. The moon is there whether or not you look at it. Anti-realism questions this, suggesting that at least some properties don't exist until they're measured. Einstein was a realist. He believed that particles must have definite positions and momentums, even if we can't measure both simultaneously due to the uncertainty principle. He thought quantum mechanics was incomplete, that there must be a deeper theory that restores this realism. But experiments have shown that Einstein was wrong, at least in a straightforward sense. Bell's theorem and the experiments testing it have proven that no local realistic theory can reproduce the predictions of quantum mechanics. Either reality is non-local, meaning influences can travel faster than light, or it's not realistic, meaning particles don't have definite properties until measured or both. Most physicists accept that quantum mechanics is correct and that nature is indeed non-local and non-realistic in this technical sense. This is profoundly strange. It means that a photon doesn't have a definite position or momentum until you measure it. It's not that you don't know these properties. It's that they don't exist. The photon is in a superposition of many positions, and measurement forces it to choose one. Before measurement, the question, "Where is the photon?" doesn't have an answer. The question is meaningless. The photon is nowhere specific. It's everywhere the wave function is non-zero, existing as a probability cloud. This leads to another philosophical question. What is the nature of the wave function? Is it a real physical object, a field permeating space? Or is it just a mathematical tool, a representation of our knowledge or information about the system? This is the difference between ontological and epistemic interpretations of the wave function. Ontological interpretations say the wave function is real. It's part of the furniture of the universe. Epistemic interpretations say it's just information, a way of encoding what we know or could know about the system. There are arguments for both views. The ontological view is appealing because it takes the mathematics of quantum mechanics at face value. The wave function evolves according to a clear equation, the Schrödinger equation, just like any physical field. But it leads to strange consequences, like the many worlds interpretation, where all possible outcomes are real. The epistemic view avoids these consequences by saying the wave function is just a tool, but then it has to explain why this tool works so well, why nature respects these mathematical predictions if they don't represent something real. Let me give you an analogy. Imagine you have a coin that you've flipped, but not yet looked at. You might say the probability that it's heads is 50%. Is this probability a real property of the coin, or is it just a representation of your knowledge? It's clearly the latter. The coin is definitely either heads or tails. You just don't know which. But quantum mechanics is different. A photon in a superposition of two polarizations isn't secretly in one polarization or the other. It's genuinely in both until measured. This has been confirmed by experiments. The quantum probabilities aren't just expressions of ignorance. They represent genuine indeterminacy in nature. This brings us to the question of determinism. Classical physics is deterministic. If you know the initial conditions of a system exactly, you can predict its future behavior exactly. Quantum mechanics is not deterministic in the same way. You can predict probabilities. Now let's talk about something that might seem like science fiction, but is actually at the cutting edge of physics research, using photons to probe the very fabric of spacetime. We've talked about photons in the context of quantum mechanics and special relativity, but there's also general relativity, Einstein's theory of gravity. General relativity says that mass and energy curve spacetime, and objects move along the straightest possible paths in this curved spacetime, which we perceive as gravity. Photons, despite having no mass, still respond to this curvature because they're energy, and energy curves spacetime just like mass does. One of the most famous predictions of general relativity is gravitational lensing. Light from a distant star or galaxy, passing near a massive object like another galaxy or a black hole, is bent by the curvature of spacetime around that object. This can create multiple images of the distant object, or rings of light, or magnified images. Gravitational lensing was first observed during a solar eclipse in 1919, when stars near the sun appeared, shifted from their usual positions because the sun's gravity bent the light. This observation confirmed general relativity and made Einstein world famous. Gravitational lensing is now a crucial tool in astronomy. Astronomers use it to study distant galaxies, to detect dark matter, and to measure the expansion rate of the universe. The fact that light is bent by gravity, which means photons follow curved paths through spacetime, is a direct demonstration that spacetime is not flat, not static, but dynamic, shaped by the presence of mass and energy. Now, let's push this further. What happens to photons near a black hole, where gravity is so strong that not even light can escape? The boundary of a black hole is called the event horizon. Anything that crosses the event horizon, including photons, can never come back out. The curvature of spacetime is so extreme that all paths lead inward. For a photon right at the event horizon, spacetime is curved so much that even moving at the speed of light outward, the photon stays in place. It's like running on a treadmill. It's moving as fast as you can run. You're moving, but you're not going anywhere. Inside the event horizon, things get even stranger. The roles of space and time swap. In normal spacetime, you can choose where to go in space, but you're always moving forward in time. Inside a black hole, you're always moving inward toward the singularity, and that inward direction becomes the time direction. You can't avoid moving toward the singularity any more than you can avoid moving forward in time outside the black hole. A photon inside the event horizon, despite moving at the speed of light, is dragged inexorably toward the singularity, the point of infinite density at the center. What happens at the singularity? General relativity predicts that space-time curvature becomes infinite, but this is likely a sign that the theory breaks down. We need a theory of quantum gravity, combining general relativity and quantum mechanics, to understand what really happens. Such a theory doesn't fully exist yet, but there are candidates like string theory and loop quantum gravity. These theories suggest that space-time itself might be quantized, made of discrete chunks at the smallest scales, around the Planck length of y-35 meters. If space-time is quantized, then photons, which are excitations of the electromagnetic field living in space-time, would interact with this quantum structure. At energies far beyond what we can currently achieve, perhaps near the singularity of a black hole, or in the first moments after the Big Bang, the quantum nature of space-time would become important. Photons might not travel in straight lines, even in vacuum. The very concept of a continuous path might break down. There's also Hawking radiation, which I mentioned earlier. Stephen Hawking showed that black holes aren't completely black. Due to quantum effects near the event horizon, they emit radiation, primarily photons. This radiation has a thermal spectrum, as if the black hole has a temperature. The temperature is incredibly small for large black holes, but for very small black holes, it could be significant. Over unimaginably long times, a black hole can evaporate completely through Hawking radiation, turning all its mass into photons and other particles that escape to infinity. Hawking radiation is a quantum effect in curved spacetime. It arises from the same quantum fluctuations we talked about earlier, virtual particle-antiparticle pairs. Near the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle is real, carrying away energy, while the infalling particle has negative energy from the black hole's perspective, reducing its mass. This process connects quantum mechanics, general relativity, and thermodynamics in a profound way. It suggests that black holes have entropy, that they contain information, and that they obey the laws of thermodynamics. This has led to deep questions about the information paradox. What happens to the information about things that fall into a black hole? Is it destroyed, which would violate quantum mechanics, or is it somehow preserved in the Hawking radiation? These are frontier questions in theoretical physics, and photons, humble particles of light, are at the center of them. By studying how photons behave near black holes, in the early universe, in extreme gravitational fields, physicists hope to unlock the secrets of quantum gravity and the ultimate nature of spacetime. Here's another cutting-edge area, using photons to test the foundations of quantum mechanics itself. There are experiments testing whether the superposition principle holds for larger and larger systems. Could you put a living organism, like a bacterium, in a quantum superposition? What about a virus? These are questions being explored in labs right now, and photons are often used to create and manipulate these superpositions. There are also tests of quantum entanglement over cosmic distances. In 2017, Chinese scientists used the Michis satellite to demonstrate entanglement between photons separated by more than 1,200 kilometers. Future experiments might test entanglement between Earth and the Moon, or even between different satellites orbiting distant planets. These experiments test whether quantum mechanics holds on the largest scales, or whether there's some modification at large distances. And then there's the search for new physics beyond the standard model. The standard model of particle physics describes all known particles and forces, except gravity. It's been incredibly successful, but we know it's not complete. There's dark matter, which we detect through its gravitational effects, but don't know what it's made of. There's dark energy, driving the accelerated expansion of the universe. There are unexplained mysteries, like why the universe has more matter than antimatter. Photons are tools for exploring these mysteries. High-energy photons, gamma rays, from distant astrophysical sources can tell us about violent events like supernova and gamma-ray bursts. Photons from the cosmic microwave background carry information about the early universe, about the initial conditions that led to the formation of galaxies and stars. Every photon is a messenger, carrying information from its source to us, and by studying these messengers, we learn about the universe. Here's the 12th mind-blown moment. Photons are not just interesting in their own right. They're tools for exploring the deepest questions in physics. They probe the structure of spacetime, test the limits of quantum mechanics, carry information from the edge of the observable universe. Every photon reaching your eye from a distant star has traveled through curved spacetime, navigated gravitational fields, survived for billions of years. It's a time capsule, a messenger from the past, connecting you to events that happened long before humanity existed. And by studying photons, by understanding their properties and interactions, we're uncovering the fundamental laws that govern reality. When you think about touching a photon, you're thinking about touching one of the most fundamental entities in the universe, a quantum of the electromagnetic field, a particle of pure energy moving at the ultimate cosmic speed limit. You can't touch it, but you can interact with it, study it, use it to explore the universe. And in doing so, you're participating in one of humanity's greatest adventures, the quest to understand the nature of reality itself. Let's bring this back to you, to your life, to your everyday experience. I've been talking about abstract physics, quantum mechanics, space-time, black holes. But what does any of this have to do with you? Why should you care that you can't touch a photon? I'm going to tell you why this matters. Why understanding the quantum nature of light changes how you see yourself and your place in the universe. First, realize that you're made of quantum particles. Every atom in your body is a quantum system. The electrons in your atoms are in quantum superpositions, spread out in clouds of probability. The chemical bonds that hold your molecules together are quantum mechanical in nature. Life itself is a quantum phenomenon. Photosynthesis, the process by which plants convert sunlight into chemical energy, relies on quantum coherence, where molecules exist in superpositions that allow energy to find the most efficient path through the system. Your DNA, the molecule that carries your genetic information, is held together by chemical bonds that are quantum mechanical. Mutations, the random changes in DNA that drive evolution, can be caused by quantum events. A high-energy photon from cosmic radiation, or even a thermal fluctuation, can cause a quantum tunneling event where an atom shifts position, changing the DNA sequence. You, as a biological organism, as a living being, are a product of countless quantum events that have occurred over billions of years of evolution. And your consciousness, your subjective experience, your sense of self, all of this arises from the physical processes in your brain, which are ultimately quantum processes. Now, as I said earlier, your brain is probably largely classical in its operation, with quantum effects averaging out. But the information that enters your brain, the photons hitting your retina, the chemical signals in your neurons. These originate from quantum events. Your perception of the world is built on a foundation of quantum mechanics. Here's a thought experiment. Right now, you're reading these words, seeing letters on a screen or page. Those letters are visible because light is reflecting off them and entering your eyes. That light is made of photons. Each photon traveled from its source, perhaps an LED in your screen or a light bulb in your room, through space, reflected off the surface, and entered your eye. Along the way, each photon existed in a quantum superposition of paths, interfering with itself, behaving like a wave. When it hit your retina, its wave function collapsed or decayed. It was absorbed by a molecule, triggering a cascade of events that resulted in an electrical signal being sent to your brain. Your brain processed millions of these signals and constructed the image you're seeing right now. You're not seeing the words directly. You're seeing the result of countless quantum measurement events. Your visual experience is a reconstruction, a model built by your brain from quantum data. In a very real sense, you're not seeing the world as it is. You're seeing a quantum-informed interpretation of the world. The colors you see don't exist out there in the world. Color is how your brain interprets different frequencies of light, different energies of photons. The photons themselves have no color. They have frequency, energy, wavelength, but color is a subjective experience, a quality, generated by your brain's processing of quantum information. This might seem unsettling. It suggests that your perception of reality is, in some sense, an illusion. But I'd argue it's the opposite. It's profound. It means you're directly connected to the quantum nature of the universe. Every moment of visual awareness is a moment of quantum measurement, of wave function collapse, of participating in the creation of reality. You're not separate from the universe, observing it from outside. You're part of the universe, a localized pattern of organized complexity. These photons you emit are created by the thermal motion of molecules in your body. Atoms and molecules are always vibrating, moving, colliding. These motions involve charged particles, electrons and protons, and accelerating charges emit electromagnetic radiation. At body temperature, most of this radiation is in the infrared. You're creating photons, new quanta of light, continuously. These photons leave your body, travel through space, and might be absorbed by something else. They carry information about you, about your temperature, about the processes happening in your body. In a very literal sense, you're connected to everything around you through the exchange of photons. You're absorbing photons from your environment, and you're emitting photons to your environment. You're in a constant dialogue with the universe, mediated by light. This isn't metaphorical. It's physics. Every interaction, every sensation, every perception involves the exchange of energy and information, much of it carried by photons. This is the 13th major revelation, and it's the most personal one. You are a quantum being, embedded in a quantum universe, constantly interacting with quantum fields through particles like photons. Your experience of reality, your consciousness, your sense of self, all of it emerges from these interactions. You're not separate from the universe. You're a temporary, localized pattern of organized complexity within the universe, a wave of awareness in the cosmic ocean. And photons are the threads connecting you to everything else, carrying information, energy, causality from distant stars to your retina, from your body to the environment, from the past to the present to the future. You can't touch a photon, but you're touching them all the time in the quantum sense. You're participating in the universe's ongoing creation, measurement by measurement, observation by observation. Every moment of awareness is a moment of quantum interaction, a moment where possibilities become realities, where the future emerges from the past. And that's far more profound than any classical notion of touch could ever be. Let's take the final step in this journey and talk about the implications for how you think about yourself, your choices, your life. I've shown you that reality is fundamentally quantum, that objects don't have definite properties until measured, that the future isn't completely determined. What does this mean for how you live? First, it means that uncertainty is built into the fabric of reality. You can't know everything. There are limits to knowledge, not just practical limits, but fundamental limits imposed by the uncertainty principle. You can't simultaneously know the exact position and momentum of a particle. You can't predict the exact outcome of a quantum measurement. There's an irreducible randomness in nature. Some people find this disturbing, but I think it's liberating. It means the future is open. It's not written in stone. Your choices matter. Now, I'm not saying that quantum randomness directly affects your decisions. Your brain is probably too warm and wet for quantum effects to play a major role in cognition. But the fact that the universe isn't deterministic at its most fundamental level suggests that there's room for genuine novelty, for spontaneity, for things to unfold in ways that aren't simply the mechanical playing out of initial conditions. Second, it means that observation matters. Measurement isn't passive. When you observe something, when you interact with it, you're participating in the process of creating reality. This is true in the most literal sense in quantum mechanics, where measurement causes wave function collapse. But it's also true in a broader sense. Your attention, your focus, your choices about what to observe and what to ignore shape your experience of reality. Think about it. You're constantly flooded with sensory information. Photons are hitting your retina from every direction. Sounds are entering your ears. Sensations are reaching your skin. Your brain can't process all of it, so it selects, filters, highlights certain information, and ignores the rest. What you attend to becomes your reality. What you ignore fades into the background. In this sense, you're creating your subjective reality through your choices about where to direct your attention. This isn't solipsism. I'm not saying you're creating the external world through your thoughts. The photons are really there, whether you observe them or not. But your experience of those photons, the meaning you assign to them, the way you integrate them into your model of the world, that's created by you. Two people can look at the same scene and see completely different things because they're attending to different aspects, bringing different expectations, different histories, different contexts. Third, it means you're connected to the universe in ways you might not have appreciated. Every photon you see connects you to its source. When you see the sun, you're experiencing light that left the sun 8 minutes ago. When you see a distant galaxy through a telescope, you're seeing light that left that galaxy millions or billions of years ago. You're directly connected to these distant places and times through the photons. You're not an isolated island. You're a node in a vast network of causal connections, constantly receiving information from the universe and sending information back. This should give you a sense of perspective. The atoms in your body were forged in stars that exploded long before the sun existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in nuclear fusion reactions in massive stars and dispersed through space when those stars went supernova. You're made of stardust. This isn't just poetic language. It's literal fact. The very substance of your body, the matter that makes up your cells, was created in cosmic crucibles billions of years ago. And the photons you see, the light that enters your eyes, some of it has been traveling for billions of years. The cosmic microwave background photons that pass through your body right now are older than the sun, older than the Earth, almost as old as the universe itself. You're interacting with ancient light, participating in a cosmic story that began 13.8 billion years ago with the Big Bang. This should give you a sense of humility. You're tiny, a brief flicker of consciousness in a vast cosmos. Your entire life, all of human history, all of recorded civilization is a blink of an eye on cosmic timescales. The universe existed for billions of years before you were born and will exist for trillions of years after you die. In the grand scheme of things, you're infinitesimally small and brief. But it should also give you a sense of wonder and significance. Despite being small, you're complex. Your brain contains about 86 billion neurons, each connected to thousands of others, creating trillions of synapses. The number of possible brain states, the number of different thoughts you could have, is astronomical, perhaps greater than the number of atoms in the visible universe. You're a locus of immense complexity, capable of reflecting on the universe, of understanding the laws of physics, of appreciating beauty, of experiencing love and joy and sorrow. And you're part of the universe's way of knowing itself. The universe, through you, has become self-aware. The atoms that make up your brain, once scattered through space, have come together in a configuration that allows consciousness to emerge. You're the universe looking at itself, thinking about itself, asking questions about its own nature. This is extraordinary. Out of the chaos of the Big Bang, out of the random collisions of particles, out of the blind processes of cosmic evolution, complexity has emerged. Stars, planets, life, consciousness, intelligence. And here you are, a conscious being, capable of understanding photons and quantum mechanics and the structure of spacetime. So what does it mean that you can't touch a photon? It means that reality is stranger and more beautiful than you might have imagined. It means that the simple act of seeing, of light entering your eye, is a quantum event connecting you to the cosmos. It means that you're not separate from the universe, but deeply embedded in it, interacting with it constantly through quantum processes. It means that observation isn't passive but active, that you're participating in the creation of reality through your measurements, your interactions, your choices about what to attend to. It means that the world is not made of solid, definite things, but of quantum fields, probabilities, superpositions. It means that the future is open, that uncertainty is fundamental, that there's room for spontaneity and novelty. It means that you're made of stardust, that you're connected to distant stars and ancient photons, that you're a temporary pattern of organized complexity in a universe trending toward disorder. It means that you're significant despite being small, that your consciousness is a rare and precious emergence, that your ability to understand and appreciate the universe is itself a cosmic achievement. And it means that every moment of awareness, every glance at the sky, every sensation of light on your skin is a miracle. You're experiencing the results of billions of years of cosmic evolution, of quantum processes that began in the Big Bang and continue in your brain right now. You're a conscious observer in a quantum universe, collapsing wave functions, creating realities, participating in the ongoing unfoldment of the cosmos. You can't touch a photon, but you don't need to. You're already in intimate contact with photons, with light, with the electromagnetic field that permeates all of space. You're a quantum being in a quantum universe, and that's far more profound than any classical notion of touch could capture. This is the final, deepest answer to the question we started with. Touching a photon is impossible, because photons don't exist in the way classical objects exist. But interacting with photons, participating in their quantum nature, experiencing the results of their destruction in your retina, that's happening constantly. And through these interactions, you're connected to everything, to the stars, to the cosmos, to the fundamental fabric of reality itself. So where does this leave us? We've journeyed from the basics of what a photon is, through the quantum weirdness of superposition and measurement, through relativity and the structure of spacetime, through cutting-edge experiments and philosophical implications, all the way to your own place in the cosmos. The question, what if we could touch a photon, has led us to examine the very nature of reality, matter, energy, time, space, observation, and consciousness. The answer is no. You can't touch a photon in any classical sense. Photons are quantum objects that don't have definite positions until measured. They move at the speed of light and don't experience time. They're constantly being created and destroyed in interactions with matter. They don't have persistent identity. They're not solid things you can grasp. But the deeper answer is that you're already touching photons all the time, in the quantum sense. Every moment of vision, every sensation of warmth from sunlight, every interaction with the electromagnetic field involves photons. You're a quantum observer, collapsing wave functions, participating in the universe's ongoing creation. I want you to walk away from this with a sense of wonder. The next time you step outside and feel the sun on your face, remember that those photons left the sun 8 minutes ago, traveled 150 million kilometers through space, and are now transferring their energy to your skin, creating the sensation of warmth. The next time you look at the stars, remember that each photon entering your eye has traveled for years or centuries, connecting you directly to distant suns. The next time you turn on a light, remember that the photons illuminating the room are being created in that instant by electrons dropping to lower energy states in the atoms of the bulb's filament or the LED's semiconductor. Remember that you're made of quantum particles, that your consciousness emerges from quantum processes, that you're embedded in a quantum universe where nothing is fully certain, where observation creates reality, where the past and future are connected by timeless photons moving at the cosmic speed limit. Remember that you're stardust, that you're connected to everything through photons and other particles, that you're part of the universe's way of knowing itself. And remember that science, physics, the quest to understand nature, is one of humanity's greatest achievements. Every equation I've mentioned, every experiment, every insight, is the result of centuries of human curiosity, ingenuity, and hard work. People like Newton and Huygens and Young and Maxwell and Planck and Einstein and Bohr and Heisenberg and Feynman and Hawking and countless others have dedicated their lives to understanding how the universe works. And what they've discovered is far stranger and more beautiful than anyone could have imagined. The fact that you can't touch a photon isn't a limitation. It's a revelation. It tells us that the universe is quantum, that reality is fundamentally different from our everyday intuitions, that there are depths of mystery and beauty waiting to be explored. And you, by taking this journey, by engaging with these ideas, by asking questions about the nature of light and matter and reality, you're participating in this grand adventure of understanding. So thank you for staying with me through this deep dive into the nature of photons. I hope you see the world a little differently now. I hope you appreciate the quantum strangeness underlying everything you see and touch.